Welcome back to the 10th session of our Circuit Programming in C laboratory series. So today what we'll be covering is called I/O multiplexing, which is input and output multiplexing. So let's first try to understand what is I/O multiplexing and why we use and why we need I/O multiplexing when we already have multiprocessing. So first, to answer the question what is multiplexing, we have to understand a single thing that we will be using in multi-server and multiple client networking case. So what I/O multiplexing does is it makes it possible for a single process server, not multiple processes, but just a single process server to serve multiple clients, to serve large number of clients. So what we're dealing with is just one process working with multiple clients at the same time. And that is possible because I/O multiplexing allows us to do so. So to answer the next question, why multiplexing? Why to use multiplexing instead of multiprocessing? Because it was working fine, right? The multiprocessing. Because the I/O multiplexing has several advantages over multiprocessing. So to say, the multiprocessing has several disadvantages over I/O multiplexing. So one of the disadvantages is frequent generation of processes leads to poor performance. That means like if the more processes you have, the worse it is for the operating system, because like it has to handle multiple, like more number of processes, and that degrades the performance of like it will be negligible, but still the better way to use networked applications is to use I/O multiplexing. But still, it depends on what kind of application you want to create. But just in case, we are going to be covering this one as well, so that you know the ways to create these TCP servers that can handle multiple clients at the same time. So the second disadvantage is it is not easy to implement because it has to be implemented considering the flow of multi-processes. When you create multiple processes, you have to know the instructions that will be executed in specific processes. Like you remember, we put conditions like if the fork's PID result was equal to 0, that would be the child process's content, the scope. Otherwise, it would be the parent process. So that makes our job of implementation more difficult than considering only a single process. So an example flow of instructions after fork function calls. So that is one of the disadvantages of multiprocessing over multiplexing, because in I/O multiplexing we are only considering one process that handles multiple clients. The next disadvantage is the server's implementations become a little bit more complex. It's the same reason, but from different point of view. It becomes more complex in situations where the communication between processes is required. So what I mean by this is as the TCP server creates multiple processes, devoted processes for each client's connection request, we are coming to the end where the processes might have to be on the server side, the processes might have to be synchronized, or for example, the server will have to stop all the communication with clients, or let's say the clients want to communicate with each other. That means on the server's end, the processes that have been created have to communicate with each other, have to talk to each other, and they're separate, so to say, separate processes. And in that case, we need the use of inter-process communications like pipes or semaphores, so on and so forth. So that makes our job of implementation more complex. So the two parts are the complexity of implementation and the performance. So in both ways, the multiprocessing is losing to I/O multiplexing. So that means we have to learn what I/O multiplexing is, right? So the good news is the I/O multiplexing explanation will not take much time. Also, it will be quite easy to understand, but that does not mean it's less important than processing and multiprocessing. It is as important as that, but it is easier to understand and it is easier to implement. So let's try to take a look how it looks like. The alternative, the analog to I/O multiplexing in real life could be telephones. Like if in your childhood you tried to talk to each other with two cups connected with a net, then you might have heard how one voice could reach the end of another cup, right? So it's basically, what I want to say with this is what you were doing is the analog of multi-process, when one person was devoted to speak or listen to another person at the second end of that telephone, right? It was working. The same thing was working because two people were talking to each other constantly, like they were separately like supporting each other, and that can be converted into I/O multiplexing. For example, like this, it can be virtual. I'm not sure if it will work in real life or not, but you can understand the networking, the multiprocessing way of implementing networking as I/O multiplexing version, like by just connecting all the cups just to one net, and that way the telephone can be multiplexed because the frequency of each of the cups' voices are different, and in the transmission and reception of data in computer networking applications in C, it will be still possible, not because of the voice frequencies are different, it's not, they're all the same, but the thing is the clients can wait each other for a little bit of time, like maybe in milliseconds or microseconds, so it does not make really much of a deal. So the explanation is like this. Similarly, the transmission and reception of data is also possible for multiplexing because it does not have to be served with zero latency in real time. Even though the clients will be sending and trying to send and receive the data to and from the server at the same time, the client will not notice the difference, time latency, that was caused due to one process serving multiple clients at the same time. That latency will not be really significant. It will be really small, so that is negligible. That's why I/O multiplexing can be supported, can be used to support multiple clients by a single server. But the thing is, like, we have a question now, generated a question. The question is how one process can manage multiple sockets, because we're just doing one process and we have to actually listen for changes. We have to sense if some client sends a message. For that we have to be listening, constantly keeping on listening to all clients, right? How can we do it at the same time on all clients? So that's the question that we have. As shown in the images, the multiplexing is the feature where we will be using a single resource that will be a single process while working with multiple ends. And we can understand it by taking a look at the next explanation of how I/O multiplexing is set up and started. That can be the support of multiple clients by a single process can be achieved by first configuring the file target descriptors for observing their change. So basically what we're doing in the step one is we're telling the operating system that I want to listen to changes on these file descriptors. And file descriptors can mean the sockets as well, because the sockets file descriptor is continued after the keyboard and screen output, console output, 0, 1, and then whatever the stream you create, stream can be the socket stream as well, that will be continued by 2, 3, 4, 5, 6, right? The numbers will be alongside all the streams, like 0 and 1, the keyboards. So we have to specify what target file descriptors we want to observe. And then after setting up, in the step 2, what we have to do is we have to request those changes. We have to check if any of the file descriptors that we wanted to observe has some changes in them. And then after that, oh, I apologize, the numbering must be 1, 2, and 3. This one is 3. It's not 1, 1, 1, of course. So the second step is requesting changes in the observation file descriptors. The last step is if any change occurs within those file descriptors, we have to get those responses, like get whatever the data is coming or whatever data we want to transfer to, because the file descriptor has some change in it. So the change can be the input and output or output change, depending on how we set up. So basically, the logic is very simple. We have to configure, we have to tell, like, I want to listen to keyboard, I want to listen to this client, I want to listen to these clients. So we'll be specifying multiple file descriptors. And then we have to request the change on the observation. And then we have to read that change that has been triggered after we request the change. So after requesting the change, actually what the operating system does is like it's going to be returning you either true or false. True if there are any changes like in any file descriptors, or false if there are no changes. So that means your single process can know if any change occurs in any of the file descriptors. So that way we'll be able to support multiple clients at the same time with a single process. So taking a look at more technical details of how to configure file descriptors. So here we're talking about the configuration step. That is the first step 1, right? It's not the step 2. We're talking about step 1 on this slide. We can do it first of all by creating an FD set, the object from an FD set data structure. The FD set data structure stands for just simple file descriptor set. It can be understood as a list of file descriptors, just an array of integers like. And that set, first we don't know what the values are provided by an operating system, so that's why we have to clear out all the file descriptors that was provided by this data structure by calling this function of fd0. What that fd0 does is it sets zeros, it sets the values of 0 to each element of this list of file descriptors. So basically what we're saying, at the beginning I don't want to have any ones in any of the file descriptors. That means I don't want to listen to any change in the beginning. Now I will specify what I want to listen to. And that now I want to listen to any change in these specific file descriptors can be specified by making a function call of fdset. It's a macro, it's not a function. So using macros like fdset, fdclear, what we can do is one can specify which descriptor change to observe and which not to observe. So here are the definitions. fd0 clears out the whole fdset, and then fdset macro. In here you specify which file descriptor inside which list you want to set to 1. This example sets the value of the fd set, the first index, to value 1. That means the file descriptor which has a value of 1 will be observed. And then we are saying fd set the second element in our set. That means I want to listen to change in this file descriptor as well, right? And later, like, we can clear out some of the file descriptors after, for example, a client has connected and like the messages were exchanged and then client has disconnected. So that means we don't have to listen to that file descriptor to which the client was connected to. At that point, we can just clear out that flag inside our FD set, and that's it. That's the setup stage. And after the setup stage, there is requesting changes. That requesting change is made by a function call called select, and that select accepts multiple arguments, and the most important ones are the maxFD. What is the maximum number of file descriptors inside your FD set? That means, like, at the beginning, if you don't have any streams or sockets or files open, the only two file descriptors always available are 0 and 1, which is the console input and console output, 0 and 1. And the maxFD will be the value of 2, like the maximum value of the file descriptors that I can be possibly listening to is 2, and like it will be the lesser than 2, that means like 0 and 1. So that's the first argument that you have to know, and then the second one is the FD set that we have configured previously. So you'll just provide that, and you don't have to worry about these two values. You can just provide 0, 0 because we don't have to be like diving deep into that much details. And the last one, which is very important, is the timeout. So now that we are working only with one process handling multiple file descriptors, we have to say if there are no changes during this timeout, like for example it can be several seconds or several seconds plus several microseconds, then don't just hang the instruction execution on this line longer than this time. So if you specify 1 second, then this function will be blocking the instruction call for 1 second, and then it will move on. That's how the your single server will not be stopping, for example, when working with input like console and the streams like server socket or the client socket streams. It will not be hanging on just one execution longer than the time interval that you specify here. The more formal definition and explanation of the select function call is as down below. The select system call tells whether there is any data to be read on the file descriptors of interest, that one specified with fdset macro. Alright, that is the end of the slide. So now what we can do is we can move on to take a look at the source codes and understand it by practice. So let's move on and take a look at the source codes. The first one is the select.c file. Let's copy it inside our cygwin folder. Home directory, your username, let's copy and paste it in. Oh, let's open up the source code and try to understand what is written in there. So, and don't forget this header file, because that one contains our the select function call and stuff. So the first thing that we're doing is actually creating an object from this data structure fdset. We're creating two of them because like we are creating originally for setup, and then we are doing like selections and stuff to like, it's a temporary object that will be storing the value of fdset. Just copy it and that's it. So we are creating the fdset, which we'll be using for setup, and here what we're doing is the step 1. We are first clearing out all the values that can be possibly provided by an operating system not equal to 0. We are clearing out by setting all of them to 0 by calling this macro fd0. And then we are saying I want to listen to the change in the file descriptor of 0, which is the standard input, the console. We are saying I want to listen to all the changes inside here. And then after this, we are like directly moving on to a while loop, because what we want is our application to be running infinitely to read any console inputs. And here what we're doing is we are copying out the value of the file descriptor, which was set up right here to a temporary memory area, and then we are selecting the change, requesting the changes that were made on the file descriptor 0, which we specified here, by making a select function call. And I want to make a note right at this point as well. This wasn't the end of the configuration step, because the configuration step also contains the time interval. That time interval has to be like, you have to know, like, it can be any time you want. For example, it can be 1 second and plus like 500 millisecond. It can be 500 microseconds, it's up to you. So we have specified that, okay, we have specified that time interval, and then we are selecting the change. That means like, we're not, no, I want to change that sentence. We are not selecting the change. We are checking if there are any changes in the file descriptors by making this function call. We're saying the maximum is 1. That means we're only considering the 0, the first element of the file descriptor set, which is the console input, and we're providing the FDS, the copy FDS, which is just direct copy of the configuration file descriptor set, and we're providing this timeout of 5 seconds and 500 microseconds. This is not necessary, it's going to be just 0 for now. And then this will be hanging on for 5 seconds if there are no changes in the console. And then we will have a value of -1 if there is a selection error. Like, it should not happen usually, like if you don't provide like invalid file descriptors. So let's just skip this point. Otherwise, if the value is valid, it will provide 0 if there are no changes in the console input, which in this case is just single file descriptor. It's not multiple, like we're just listening for one file descriptor. So we have 0, that means there are no changes, and if it's not equal to 0, and if it's not equal to -1, it will be equal to 1, which is the value equivalent to true. That means there are changes. The select is returning true. If the select is returning true, that means there is some change. And Now we're just making sure that the changes in the 0th file descriptor by making a call to this macro. fd is set 0. We're checking if this is set, if we're really listening to the change of the console, the changes in the console. So what we're doing is we are reading a value that was provided to the file descriptor 0, which is in our case just the console. We are reading a value from a console, storing it inside our buffer, which was created up above right here. We are storing the value here, and we are like putting a termination character, and then we are printing out that message that was received from a console. So this seems pretty easy to understand, doesn't it? Let's try to compile and see how it looks like. gcc-o select.c, and if we run it, what we will see is the first thing that I will show you is when we don't make any change during 5 seconds, we need to be seeing the timeout message printed out like again and again and again and again until we input some data. So what I want to see right now is I don't want to enter anything, and I want to see the timeout. So 1, 2, 3, 4, 5. Come on, okay. So there it is. So now we can see that the process, the single process, is not hanging up to like the input like all the time, right? It's checking if there is any change, but it's not hanging to that. It's not stopping the execution. So what we can do is like at any point, let's say, let's wait for one more timeout and print out something. So there it is. Like it's not hanging. It's not that the process is keeping on its execution right at the point when we enter the data. So that can be exploited when we work with multiple clients. So exactly in the same fashion, our TCP server, our TCP server is going to just check if there are any changes on the client socket file descriptors. If there are no changes, it will just keep on looping through again and again and again and again. That means the server process will not be dependent on when a client sends a message. So that's pretty cool, right? The server is independent. And so let's just skip the beginning points, which I have previously covered already. About the TCP, it's just simply creating file descriptors for server, TCP server socket, and creating the variables for address, creating the buffers. And here, this point is, the FD max is the number that we have put as 1 in this point in the source code. At this point, like we have just provided a value of 1, which was the max FD variable. And now that we're not just working with a single file descriptor, what we have to do is we have to have some variable to count how many clients we have, how many file descriptors we have created. So that's why we have created this variable of fdmax to provide it to the select function call finally. So let's keep on continuing from this fdmax line of code. After this, we are creating our server socket, which is TCP, and providing the address that was received from a console as an argument, and we are binding, we are listening. And at this point is the point of setup of I/O multiplexing. We are first clearing out, let me just go back and show you where the variable was created. Right here, the variable was created, the file descriptor set was created right here. We also like the one that we copied in the select.c file as well, just like exactly the same way. And here we are setting it up with we are clearing out every file descriptor inside the set with a macro called fd0, after which we are saying the first socket that I want to listen to is the server socket, and then we will still keep on configuring it on the way down below when clients try to connect. So basically the first communication, the first configuration step is to listen to the server socket's changes. That means we want to know when clients want to connect, when clients call a connect function call. Like you remember the clients connect function call. When clients make this function call, we will be seeing the change in this file descriptor. If it makes sense, let's continue. By far the maximum file descriptor is the server socket, which can be the value of 2, but we are not going to be providing the value of 2 to select, but we are going to be providing the value of 3, because the 2 which must be included. So that's why it's FD plus 1. So we are, after selecting the FD max value, we are starting to loop through the content of our TCP server. This is the content of looping. And then inside here we are saying I want to or my instruction I want my process, my single process, to wait for change inside the file descriptor set for 5 seconds and 5,000 microseconds. Let's change it for now so that not to confuse, like 0 microseconds and 2 seconds. Just we're going to be making our process hang for 2 seconds. And then what we're doing is we are selecting if there's any change that will be returning true or false or -1 in case of error. So let's consider the error case will not be there. So the value is either 0 or 1, right? If it's equal to 0, that means there are no changes, right? So if there are no changes, then continue looping through the while loop because there are no changes, and keep on listening if there will be any change. So by far, if you've noticed, we're only listening for the server socket, right? If clients make connection requests, not the data, like after. The interesting question is what happens after clients connect, right? After clients make a connect function call, this will not be entered. That means we will be moving on to the for loop. And what that for loop does is it loops through all the file descriptors that was specified, that we are keeping track, which was in the beginning 0, the 2. And here we are saying like until FD plus 1, that means the server socket will be included as well. And we're checking if the file descriptor is set. So that's the reason why we are using the isSet. You might have that question, why do we have to use isSet? Because we must already know which file descriptors we have specified. But here we're using isSet because here we only specify that we want to listen to the file descriptor 2, not 0 or 1, right? Like not 0 or 1, not the input console and stuff, but the server socket. And this for loop, this for loop is looping through all the file descriptors starting from 0, and that 0 is not set. That's why we have to check if that's the file descriptor of interest. So here comes the keyword of interest. Is the IF file descriptor the one of our interest? So here is the meaning of this FD is the one file descriptor we are listening to in this file descriptor set. If it is, then do your job. So the first thing is, if the I is the server socket, that means there has been a change inside server socket. That means it is a connection request. There will be a change inside server socket if there is a connection request. So this scope will be the scope of accepting the client's connection requests. So let's first consider only this case, and then we'll move on to the next one. So what we are doing inside this scope is we are taking the client's address. We're creating a variable for storing the client's address, and we're providing it inside the accept function call, and we are doing it with the server socket file descriptor, and we get the client socket that will be that must be also listened by an operating system, so that it would tell our process that there has been any change inside the client socket. That means the client has sent any data to us. And we are configuring one more time the file descriptor set, specifying this client descriptor, file descriptor, and then we are updating the FD max because we have one more file descriptor added, right? And what we're saying is, if FD max is smaller than the client socket file descriptor, that was in the beginning the server socket file descriptor, which was 2, and in this case I think it will be 3, or maybe it can be 4, maybe it can be 5. I don't know. It depends on like what the sequence of the streams are open. And if it's smaller, then update it because the maximum number of file descriptor has changed. And here we're printing out that the client has connected. Otherwise, here is the other case when the file descriptor was not the server socket. And the only file descriptors that we are listening throughout this code are the server socket, right? The first FD set is the server socket, and the next FD set is the client socket. So there are only two cases: when clients connect and when clients send a message, right? When clients send a message, we will be inside this case. When the I is not equal to the server socket, it's equal to the client socket. But we don't know which client it is, but it's not important because the file descriptor is already specified here. So through the value of I, we know which client has sent us a message, because each file descriptor stands for a separate client. And here we're reading the message that the client has sent us, and then if the number of bytes that were sent by a client is equal to 0, that means the data part was equal to 0. That's the close request. The client, if you remember the fin message, data part is equal to 0 because it has a flag of fin, right? That packet will contain a data of size 0 bytes, and if the amount of bytes is equal to 0, then what we have to do is we have to close that client's connection, client's file descriptor, and we do it by closing, right? Just making a function call to close, right? And before it, like, what we have to do is we have to set our IO multiplexer not to listen to that file descriptor anymore, because we are closing it, right? We don't want to be listening to it like continuously because the connection has already been terminated. Otherwise, if the amount of data is not 0 bytes, that means there is a message. And the meaning of this source code is echo server. And whenever a client sends a message, we have to send it back. And that is it. That is all. That is very simple. That makes us echo select servers implementation. And the echo client has no difference from the previous lab sessions implementation. It's just getting an input, like creating a socket, connecting, and getting an input from a command line, and then it's just sending it to the server and receiving it after this and printing out on a console. That's just basically the echo client implementation, the basic one. And if the client enters queue, it's just stopping the execution. So that's what we wanted to see and understand. I hope you understood what's going on. Let's open up 3 terminals so that we would have multiple clients, just 2 clients, trying to connect to a single process server, which will be right here. And just make a note that we have not called a fork function call. That means we are only working with a single process, which is IO multiplexing. So let's compile and see the output. gcc-o server echo. So I think I might have, oh, it's not the folder that I wanted to put it in. It's inside the Kevin, the username. So we have the source file here, echo select server. We have compiled the server part. Let's compile the client part right here, gcc-o echo client. We have the server and client already compiled and ready. Let's run the server first, 4444. And now that the server is ready and running and waiting for any change on this server socket, let's make a connection, a request onto that server socket just by running the client 127.0.0.1.4.4.4.4. So now we can see that the server has noticed a change in that server socket, and it's printed out that one client has connected, and that 4 is the file descriptor of a client socket. It was 4, it was not 3, as I said in the source code inside. So let's try to connect another client. So if this client can also connect directly like this, that means, and then if we see a connected client 5, that will mean that IO multiplexing is working equivalently like in multiprocessing, which has just happened. Multiple clients have connected at the same time, and our IO multiplexer is now listening for any messages that must be coming from clients. Let's try to send messages simultaneously on two clients. Like this one sends, it's receiving, it's working. This client is also working. What this tells us is that I/O multiplexing methodology is as powerful as multiprocessing, with some advantages over multiprocessing, like the performance and complexity. And if we terminate a connection, the server says the client has terminated, the one client has closed, and we are not listening to any data that's coming from the file descriptor 4 anymore. And let's close that one as well, and we can see that the server has noticed both messages and connection requests and close requests. So that wraps up our today's session. Thank you for paying attention. See you on the next lab session. Bye.